Hello, so if you remember in the last video we kind of derived this formula. We talked about what method of successive approximations is actually useful for. It's not useful necessarily for finding a solution, but it's useful for suggesting whether there is actually a solution that exists. Okay, but I always think that sometimes with these kind of things, it's quite difficult to get it into your head until you actually see an example. So I'm going to talk you through an example. So this is the example we're going to look at. Okay, so in other words, we've got the first derivative of y is equal to ay. Okay, and we've been given these initial conditions here. So y naught. Okay, so so remember that the initial conditions will determine what goes here. Okay, because I showed you how to derive that, because effectively this is just a constant, this is just a plus c, okay, but when you put x equals 0, in this case I've just changed x to 0, it doesn't matter, just our independent variable, hopefully you can see that our independent variable is now x. Okay, it doesn't matter, you can call it anything you want because it's not defined in the question, but I've just defined it as x, just to show you that you can define it as whatever you want. If it's not defined in the question, you can define it as w or whatever, but normally we define it as t or x, that's more familiar independent variables that we define it as. Okay, so if you remember the method of successive approximations, I outlined it in the existence and uniqueness theorem video. Okay, the idea is that basically we put something in here on the right hand side. So this is, if you like, our function. So we've got, if I just draw this out again, so we've got the input. Okay, we've got some kind of function. Well, here our function is this thing here on the right hand side. Okay, so this thing here on the right hand side. Yeah, and then basically we get an output out, and the idea is then we just form a loop. So that output then becomes the new input, and we keep forming this loop, and then eventually what we'll end up with is that the input is the same as the output. Okay, and then once we reach that point, we know we found the solution which we're after, or at least if we get a value which is relatively close, so that they're relatively equal, then we found something, or we may find a nice pattern which enables us to then stop. Okay, so let's have a look at this then. So basically what we want to do is we want to put something, basically what we want to do is put something in here on the right hand side. Okay, so basically we want to replace this y of s, we want to put a function in here. So we only have kind of something involving, we want to basically put something in here. Well, what is this f here? What do we want to replace in this integrand, or in this integral? Okay, well we want to replace this here. Okay, that's our right hand side, but we want to put basically a value for y in. We want to put a value for y in. Well, do we know a value for y? Well, yes, we do. We know that. That is a value for y, right? Because that is basically saying that y at some particular point, in this case it's t equals 0, is equal to y naught. So we've got a value for y. We want to basically replace this for y. So in other words, what I can do, maybe if I just write this out properly, rather than talking fairly abstract. So basically this here is the right hand side. It's always the right hand side because it's of the form, first order differential equation which involves something involving y and t, okay, for example, or in this case it's x. Okay, so it's basically, this is the form that we've got, okay, and this thing here goes inside the integration. Okay, it's the integrand, it's the thing we're integrating. So in other words, what I can now do is just replace this with my right hand side. So ay. Okay, but with the method of successive approximations, we need to start off with something. We need to start off with an input value. If I draw that, if you remember that thing we had. Okay, so this thing, we need a starting value, if you like. We need something to start. In other words, we need to jump into the system. We can't just, it's all very well and good sort of setting up this loop. Once we've got a value, once we're actually into the system, once we've actually got through the door, if you like, over the first hurdle of actually putting a value in, then we're into this loop quite easily. But we need to find a value to actually put in the first place. We need a starting value. Well, do we know a starting value? Yes, we do. We've been given one in initial conditions. Because basically what this is saying is that our function at some particular value is equal to some value. Okay, so the function at t equals 0 is equal to y naught, which in other words means that we can start with y naught. That is a value that we know. So in other words, our first iteration, okay, I'm just going to call it y0 of t, okay, is going to be equal to y naught. It's going to be equal to y naught. So when I plug this back in, basically the idea is that when I plug this back in on the right hand side, so let me just try and show you. Okay, when I plug this back in on the right hand side, so when I replace this thing inside my integration with the thing, you know, with my starting value, with my y0, that's the thing which I always do. This is just some constant value, so we don't change that. But this at the moment, this before when I put that there, was just some function. Okay, so the starting function that we start with is y0. We start with that value for, you know, that's my starting function. Okay, but that basically, you know, by evaluating that thing on the right hand side will give me my output value, my y1. Okay, it's like, you know, this is my input value, this is my output value. Okay, by putting my input value into the function, I'll get my output value out. Okay, and then the idea is then that sort of once I evaluate that, so what is that? Well, okay, so y0 is just some value, right? So we're going to have y0, so that's going to remain the same, plus, what is this integration? It's basically saying a times by some value, so a is just some value, y is just some value, okay? So in other words, what we need to do then is we need to integrate that, so it's just, you can just treat this as like a constant, effectively, with respect to s. So effectively, this is a bit like saying, what is the integration of, I don't know, 3 with respect to x? Well, it's going to be 3 times x, yeah? So it's going to be exactly the same thing, because this is just going to be, this is like our 3, it's just some constant value, so it's going to be a y0, okay? But we need to integrate with respect to s. So basically, in other words, this is going to become an s, okay? And of course, we need to remember our limits of integration. We need to remember our limits of integration, so from 0 to x, okay? So I've literally just integrated that thing there. That's all I've done. So what is that now equal to? So we've got, that's equal to y0 plus, we just put these limits back in for s. Okay, replace s with these limits. So in other words, we've got a y0, okay, times x, yep, minus, so that's when we put x back in, minus, then we put this one back in. So we've got a y0 times 0, okay, so that thing there is all going to go, to 0. Okay, so it's just going to be left with a y0 times x. Okay, so that's what y1 is equal to. We found found a valuation for y1. Right, so I'm just going to tidy y1 up a little bit. So I'm just going to basically say that, well, then y1 is going to be equal to y0 lots. I'm just going to factor out y0. Okay, y0 becomes 1 plus ax. 1 plus ax. Okay, so that is now my new input function into this thing. So I'm going to now replace y. I'm going to replace this y in here with my now y1. Okay, so let's have a look. So all I'm going to do then is just replace my y1 in here. So I'm going to just then put y1 in here. So what's this going to be equal to? So it's going to be a lots of, let's see if I can fit this in, a lots of this thing here. So I'm just going to place y1 in here. So we've got y0 lots of 1 plus ax. 1 plus ax. Okay, and then it's just a case of integrating that thing just like we did before. Okay, in actual fact, I think this might be easier to expand out. So we've got, oops, don't forget to change back to your dummy variable. So this is no longer an x, it's an s, because of course, you know, that's our dummy variable. So we've got s in there. So let's have a look at this. So I'm going to actually expand this thing out. So it's a y0 plus a squared y0 s, yeah? Plus a squared y0 s. So I'm just literally multiplying through by a y0 there. All right, because that just makes it easier to integrate, right? It's got two terms which I can integrate quite simply. Remember that a y0 is just going to be a constant. So in other words, we've got y0 plus, what's this going to think? So a y0 is just a constant. So in other words, we end up with a y0 times s, because of course we're integrating with respect to s. So let me just put that in green. So this is s, okay. Plus, just remember that a squared and y0 is still going to be a constant. So a squared and y0 is still going to be a constant. But now we're integrating with respect to s. So what's the integral of s? Well, it's going to be raise the power by 1 and divide by the new power. So this is going to become over 2 s squared. All right. And of course, we've still got the limits from 0 to x. Okay, and it's just a case of putting those limits back in again. So let's have a look. So we've got y0 plus, let's just replace s with x. So we got, first of all, we got a y0 times x, okay, plus half a squared y0 times x squared, yeah, times x squared. And then we've got to do the same thing, but then we just got to put minus in. Just got to put just got to put 0 in. Are you happy that if I just replace that with 0, then both those terms will just go to 0, because it's just going to be multiplied by 0. So I'm not going to bother writing it out. Okay, So let's just kind of have a look and sort of see at the moment, see if we can spot any kind of patterns, all right? Because that, to me, is screaming something at me. It's screaming something out. That, to me, looks like a power series. Yeah? Particularly if I rearrange this, if I write this y naught, if I take a y naught out, okay, so I write y naught out, so 1 plus ax plus a half a squared x squared, yeah, and then particularly if I just take out a power of 2 from those two things, so in other words, just write that as all squared. Can you see that's a power series? So remember, this is y2 now, because of course I'm evaluating y1 in my thing, so I'm getting y2 out. So y2 is equal to something like that. So it kind of seems logical then that if we keep going, we're going to end up with a power series. And you can keep going. You can evaluate y3, y4, y5, and you can verify that actually you'll end up with a power series. So what I'm basically saying is that then yn, okay, so in other words, our solution that we're after, or sort of, you know, an indication of whether there is actually a solution, is going to be y naught lots of 1 plus ax plus a half ax squared plus 1 over 3 factorial, which is 1 over 6, or I'll write 3 factorial just for you, ax all cubed, okay, plus, then we'll keep going, so 1 over 4 factorial times ax to the power 4, okay, and we can keep going. We can keep going until we end up with, so we'll end up with the nth term, which is 1 over n factorial ax all to the power of n. Okay, so in other words, because we found a power series, and notice as well, you know, this power series here is something very, very special. It's something very, very special. It should be screaming out at you if you've studied power series before. But basically, it's the power series for e to the x, right? Because e to the power of, well, if we write out the power series for e to the power of t, it's a nice one. It's 1 plus t plus a half t squared plus 1 over 3 factorial t cubed plus 1 over 4 factorial t to the power 4, and so on and so on. Okay. Well, if I replace now t with, well, here I've got ax. So if I replace this t with ax in here, then I'll have to replace this t with ax in there. Sorry, ax in there. So I'll also have to then replace ax in there. Yeah, and ax in there, and ax in there. Okay. Can you see I'm getting exactly the same power series out, except I've got a y naught being multiplied at the front. Got y naught being multiplied at the front, so then I've got to multiply a y naught there. So in other words, what I'm basically saying is that yn, my solution yn, should be the power series, so y0, e to the power of ax. That is what I'm saying, my solution, you know, I've found a solution, so therefore I know that a solution can be found for my original thing, you know, my original first order ODE. Sorry, this is a y. Okay, my original first order ODE. You know, because I've found a solution using method of successive approximations. I'm not saying this is necessarily the solution, but I'm saying that because I've found a solution, then therefore there is a solution that exists. And because I've been given some initial conditions, okay, these were the initial conditions that I was given with, then there must exist a unique solution. Okay, so if I didn't have those initial conditions, by the existence of uniqueness theorem, okay, I'm just basically summarising what the initial the existence and uniqueness theorem. Basically, if you followed everything that I've done in this video, you've got the existence and uniqueness theorem in your head. Okay, but basically what I'm saying is that using the method of successive approximations, I can find out whether there's actually a solution that exists. Okay, but then if I'm given some initial conditions, then I know that solution, that if there's a solution that exists, then it must be unique. Okay.